Okay, who has started on the Flask portion of the TwitterBot project so far? Hands have to be higher, otherwise I can't see them between the computers. Okay, some people. So I don't assume that you have any previous Flask knowledge for this part of the curriculum. I essentially have a starter project that already implements a subset of the API that you need, and I think long enough instructions to get you started, even if you didn't get to the TwitterBot part of implementing the Flask server yet. So what we want to go over as part of this lecture is basically everything you need to know about building a custom API server for your iOS app. As I said, as an alternative to using a framework like Parse or Firebase. As part of that, we're going to cover client-server communication. That just means actually looking into the details of what does a client do, what does a server do, what are the protocols and kind of the requests that go between these two parts of our app. Then we're going to look into the motivation of building a custom backend. Then into the specific technology that we're going to use for that. In this case, Flask and MongoDB as a database server. Then I want to talk a little bit about how we're going to define the API, which kind of approach we're going to use for that. And lastly, I want to talk briefly about the development technique that you should be using for building the server. So first of all, let's talk about client-server communication. Essentially, there are two very important parts to it. The first one is serialization. The second one are network requests. Who has heard about serialization before? Not so many people? Cool. Then I have a few more slides on that. So serialization, we're going to cover that first, is essentially transforming your object graph that you have in memory into a representation that you can store to disk or that you can send over the network. Most of our systems that we work together with, like the internet, for example, most communication over there is based on text. So most of the protocols were basically written in a way that you can send emails or you can download websites, but they were not really intended to send binary information. Yes? Core data also does this, yes, but it's a little bit a different aspect of that. Yeah. So essentially, you have objects in memory, and let's say you have a Swift application, then these Swift objects are encoded in a specific way that only a Swift program will understand. If you want to talk to a server that is written in Python, then it will not understand your Swift objects. So you have to transform these Swift objects into some intermediate representation that ideally is in text format, so you can send it to the server, and then the server will take that text representation and turn it into Python objects. So when you communicate between these two different technologies, you need some format which both sides understand. And turning that object graph that you have in your application into this shared format is called serialization. Here's a short diagram that shows that. Let's say you have an application that has user objects and it has product objects, and you want to model purchases of products by different users. Then you would have Swift objects, you would have a user class, you would have a product class, and at some point you would have to turn the objects that you have in memory into something that the server can understand and that you can send over a network request. And that is called serialization. The example here of the serialized document is a serialized document in JSON format. That is just one of the many formats that you can use that is understood by many different platforms and many different languages. So the only goal here, as I said, is taking our proprietary representation of objects and turning it into a document that can be understood by different parts and different applications. So serialization is the first aspect of basically implementing client-server communication. The second aspect is the network requests that actually transport that information between the different parts of our app. And to understand that in more detail, I want to talk a little bit about the architecture that goes into building an app that has a client, a server, and a server database. And classically, we used to talk about different topologies of server applications. So you can imagine there are different ways to implement a server. And the typical one that used to be around for a very long time is this classic three-tier architecture. In this three-tier architecture, you have a client. And that client is mostly concerned with representation. So it doesn't have a lot of logic. It just really is a screen and a keyboard that allows the user to input something and a screen that displays the responses. And that is how it used to be like in super, super old, what we used to call terminals. So the terminals themselves didn't really have any logic. It was really just a screen and a keyboard. And as soon as a user would type in a command, that would be sent to some server that was far away, some kind of mainframe. That would do the actual calculation, and then send a result back to the client and would be displayed on the screen. And as part of that, the servers often would use a database, because a database is a specialized piece of application that is really focused on storing information. So that is kind of the classic three-tier architecture. You have this thin client that really doesn't do any computation. It just talks to the server and asks for a certain program to run. And the actual logic is implemented on the server, and the server maybe still talks with a database to retrieve and store data. This is also in the early days of web applications what it used to look like. The thin client in that case would be your browser, and the only thing the browser would do is send a request to a server and wait for a response. These days, applications have gotten a lot more complex. So we have more of a modern three-tier architecture that looks very similar, but one of the core differences is that we have a lot of client logic as part of the application as well. So if you took part in the Summer Academy and you built an app with parse, then a lot of your apps will be useful even if they don't use the internet. So you have a lot of apps that have some kind of local logic, have some kind of caching, and you can use them without an internet connection. But you also have internet connectivity to synchronize local things to the server. So it's kind of a mix where you have logic implemented on the server, you also have logic implemented on the client, and you have to spread out business logic between the two tiers. So the client has become what we call a fat client, because in many cases also has application logic. The amount of business logic on a server can be very, very different based on different types of applications. If you use parse, for example, then in most cases, your server is just a glorified database, and all it does is just take the requests from the app and store them on the database, and it gets objects from a database and sends them to your client. But there's not a lot of logic happening on the server, in most cases. So if you use parse frameworks, then essentially your server is just a simple database. In contrast, we have apps like Twitter, for example, where still a lot of the logic lies on the server. They basically do a lot of calculation to see which users see certain tweets, which hashtags are trending. All sorts of logic is on the server side. And the client is more of a thin client where there's not too much logic. It just displays the tweets that it gets from the server. There's still some logic, but it's much less than in an application that uses parse, where the most logic is on the client. So it's not as simple as it used to be. You have business logic on both the client and the server. That's the type of app that we're going to build. So this slide here is pretty big because it covers the entire request cycle, what happens when you tap a button in your app and you want to communicate with a server. But I think it's very useful as a reference. I want to run over that really quickly. So if you have an app that communicates with a server, and in this example here, you say you want to get a list of users that use that app, then you will start by the user interacting with the UI. Then, to get the user list, you will issue an HTTP request. That HTTP request, we'll talk about it in more detail on the next slide, is basically an instruction for the server of which kind of information you want to retrieve. You send that to the server, and once you have built that Flask server, you will know which Python function shall get called that maps this HTTP request. In this case, we have a Python function called getUsers that is responsible for getting a list of all the users. As a next step, this function here will access the database to actually get the user records out of the database. Then the database will return that to the Python application. Then in this step, the Python application takes these users and now again has to perform serialization. So we have Python objects, but we have to represent them in a way that the Swift application here can also understand them. So we again serialize them into some intermediate format. In this case, again, a JSON document. So this JSON document is pure text that represents these Python objects that we got from the database. Then we return that to the client. The client now has to take the text representation and again turn that into Swift objects, because that is what we work with inside of our Swift application. Then maybe as an optional step, you also want to store that in a local database so that the app can store and access these users without that it has to ask the server again. And as a last step, you will display the users on the screen. So there are many steps that are involved, and all of them involve serializing things and deserializing them. But once you have a grasp of this, you basically understand like how almost 80 or 90% of networked applications work. These are all the steps that are involved. Is there anything unclear about this? Sorry? Where do you find the slides? I realized that I didn't follow yeah, they're basically in the iOS slides, in the iOS section, step 3. I'm going to also put them in the slide section so they're together with all the other slides. Yeah, because the text here is a little bit small, but the concepts are more important. You can look at the details later. Okay. I mentioned the term HTTP request without that I really talked about the details of that. Essentially, HTTP is a protocol that is used for most internet applications these days. It is just a specific format of how you communicate with another computer that is far away. And you send messages that are called HTTP requests that have a specific format. And in that specific format, there are different fields of things that you can send to the server that the server needs to fulfill this request and send a response. The first one is called a URI, that is a Uniform Resource Identifier. And a URL is a specific form of a Uniform Resource Identifier. All this does is it tells the server which specific resource you are interested in. So if you go to a specific website and you go to a subsite of that website, let's say makeschool.com/academy, then that is the URI, and that tells the server which part of the application it shall return to you. A second aspect is an HTTP method. We're going to talk about that in the API design section a few slides later. But essentially, the HTTP protocol defines different methods that tell the server what you want to do with this resource that you specified. So you can say, I either want to get the resource, or I want to modify it, or I want to delete it. Then there are some additional header fields. So that's what we call metadata. These are not always necessary, but sometimes they are required to serve specific requests. Some examples are authorization headers, for example. So if you have a request where the user has to enter a password and a username to get access to that, then you have to pass on a specific header to the server so that the server can validate that the user actually allows to access that resource. We're going to talk about that in a lecture this afternoon in detail. And another one that is often used is the content type header field. So HTTP can basically send and retrieve a lot of different types of contents. You can upload images, you can upload text, you can upload JSON documents. And the content type header tells the server which type of content the client is sending to the server, so that the server knows how to parse that information. And optionally, you can also send a body as part of this HTTP request. So if you actually want to save something on a server, let's say you want to upload an image, then you will store the image in the body of this HTTP request, and that is how the server will get the information and then store it to disk. These are the most important aspects of an HTTP request. So now let's look into how we're going to build a custom backend for the trip planner project, and first of all, why we're going to do it. So the first aspect that is really important for this assigned project is that we're going to do more custom and self-written code than you usually would have to do in a project, because it's a great way to learn. A lot of iOS developers that are out there that just started on their jobs often don't know how servers are implemented. And I think it's really an important aspect that helps you, even if you only want to focus on your iOS app, in understanding what goes into client-server communication. I think it's really useful to understand how you build your own API, even if you don't want to do it on the job. A second important one is flexibility. As I said, frameworks such as Parse are great to get you started. But if you have a very custom application that has specific requirements, you'll often get to a point where implementing it with Parse will get more complicated than rolling your own solution. So understanding what goes into it is really helpful for your own side projects as well. So how are we going to implement it? We're going to use two technologies. One is Flask. Flask is basically a simple framework written in Python that adds some functionality to Python that allows you to deal with HTTP requests, HTTP response, JSON parsing, and so on. And as database, we're going to use MongoDB, which is a document-based database. So as part of one of the later semesters, we're going to talk about databases in a lot of detail. But since I mentioned a document-based database here, I want to give you a very brief overview of two different types of databases. One is relational, and one is a document-based database. Has anyone here worked with databases before? Relational databases, keep hands up. And document-based databases. Okay. Cool. So essentially, these are the two major players at the moment, and they have a fundamentally different approach on how they structure data. First, let's take a look at a relational database. That here is a little bit small, so if you can't read it, it's not too important. But the essence of a relational database is that it is based on relations. So you have, for example, you want to build an application where, again, a user can buy certain products, and you want to keep track of which product a user bought. Then you would have 3 different relations in a relational database. One would be a user purchases table, where you store the user ID and the product ID for each single purchase. The only thing you store in there are IDs. Then you have a user table, where you have a user ID, and you have the additional information for that user. And you have a product ID, you have a product table, where you have a product ID and additional information for that product. So the idea is that each table represents only one specific entity. So there's a product or a user table that is distinct. And if you have any relationships between them, then you create separate tables that represent only these relationships. So in this case, the purchase table that creates a reference between the user and the product that the user bought. We also call this data model strongly denormalized, because we don't have any redundant information that is spread across multiple tables. The information about the user is only stored in the user table. The information about a product is only stored in the product table. And the purchases table only stores IDs to these 2 different entities. We would not call it denormalized if the purchases table would also have additional information about the user. So if the username would be part of this cross-referencing table here, then we would call it, then it wouldn't be a denormalized model anymore, because username would be duplicated amongst different tables. And we'll see that that is basically the approach that document-based databases use. So besides IDs, we don't have any redundant information. And that also has some downsides. That means if we want to, for example, for a specific product that has been purchased, want to get the usernames of the users that have bought this product, then we have to do a join between different tables. That means we have the user purchases table where we have a user ID, but then we have to look up in another table to get the username. If the username was stored inside of this product purchases table, then it would be much easier to get access to it. With this approach, we have to join with another table and look up the user information in there. So the advantage is that we basically don't have redundant information, but the downside is that if we want to get information about something that is not stored in our table, we have to join a lot. And that's a fairly expensive operation. So another aspect is also that the schema of these relational databases is strict. The schema means basically the fields that each entry can have. If you have a user and the user has a username, an email address, and a profile picture, then that is a schema that you have defined. In most relational databases, that schema is defined once, and if you want to change it, you have to run a migration. So you can't just add additional fields on the fly. That has downsides and upsides. The upside is that if you have an app that talks to the database, you will always exactly know which fields that database entry has. If you know there are only 3 fields, then you don't have to check if there are additional fields or if there are fields missing. You can always know that a schema is in a specific format. And the normalized model makes writing to the database easier. So if I want to update a username in this application, I only have one single place in the users table where I have to go in and change the record. We'll see in a document-based database that is strongly denormalized, we actually have to update usernames in multiple places in some cases. So the upside of this model here is we don't have redundant information. That means if we want to do changes to information, we only have to do it in one place. The downside is that we have to do join operations to get information that is not stored in our table, and that can be slow. And the strict schema can also be a downside, because if you have an app and you want to add just an additional field, you have to run a migration, which is a little bit more of a complex operation. And you'll see in a document-based database, you can just add and remove fields on the fly without that you actually have to change the schema. So the example of a document-based database is MongoDB. That is the database that we're going to use in our application. And it's very similar, the way they store information is very similar to the JSON format that I showed you earlier. So essentially, what you store in a database is not relationships, you just store documents. And here's the same example where we store the purchases of a specific user in a document format. And here you can see that we have a user ID and username at the top of this entry. But we also have the product details stored as part of the purchases here. So when we want to see which products did the user buy, we can take a look at this document, and we'll see the user bought an Apple TV, and the user bought a kitchen set, and the details of the product are stored directly within this purchase record. This means on the counter side that if multiple people bought an Apple TV, then in each of their purchase receipts, there will be the details of this product stored within them. So if the product name changes, we can't just change it in one place, but we would have to find all users that bought an Apple TV. Then we'd have to go in each of these documents and change all of the individual records. So instead of just storing an ID, we have the full information of the product here, and that means we have a lot of redundant information, which means if we want to update it, we have to update it in multiple places. On the other side, reading the information here is much easier because we have the entire document in one place. If I want to get the name of the product that a user bought, it's already in the same document, and I don't have to join it with another piece of my application. Is the difference here more or less clear? See some nodding? Cool. So that is what we call a strongly denormalized model. That means we have a lot of redundant information. The product information is stored within every single record. That means we can read faster because we have all the details within the document. We don't have to reference other documents to get the details. But it also means slower writing in some cases. And with MongoDB, when we use this document-based format, we have a flexible schema, unlike the relational databases where we have a strict schema. That means you can always add any type of entries to this record here. You can add another field to a product, you can add another field to a user, and the database will accept these additional entries without a migration. The two examples I showed here are also very extreme. You can use both types of databases with different degrees of normalized data models. So you could still have this and only have the product ID in here. But I'm showing you kind of the extreme cases of how typically document-based databases are used and how typically relational ones are used. And in a document-based database, you don't have tables and entries. You have collections and documents. So if you want to store, for example, users, then you'll have a user collection. Within these user collections, you'll have user documents that store the details about the user. That's just the terminology that you use when working with document-based database. Collections and documents. So to the benefits and drawbacks of document-based databases, as I said, there's no schema. That has an upside. It's easy to add additional fields, for example, to a data model. The denormalized model makes it easier to read information. As I said, if you want the product details of a product that a user purchased, you have that information within the document that you're looking at. You don't have to join with other parts of your database. But it also has some downsides. If you want to update information that is stored redundantly, you have to find all the places and then update the information there. And not having a schema also has a downside. If you can just add additional fields or remove fields from the database, then your application will have to deal with specific cases where fields are missing or additional fields are available. So basically, these document-based databases became very popular because they were schemaless. And a lot of people thought it's much easier to just change the schema on the fly. But it turns out that your application still will have to deal with missing fields or additional fields at some point. So it just kind of moves the schema validation from the database to your application. So it has advantages and disadvantages. It's not there's no clear winner between these two. But if you start a small side project, working with a document-based database will mostly make you a little bit faster at the beginning. So it's a good place to start. And then if you run into problems using that, a lot of companies later on when they scale up migrate to a relational model. Okay, any questions on this short detour on databases? If not, then we'll get into details of the Flask web server. Yeah, a question? MySQL, for example, or basically all SQL databases are relational ones. No, I mean, there are some, it's kind of a weird terminology because SQL is actually the name of the query language, not of the database. So recently there have been some databases that use SQL to query document-based databases. The terminology there is a little bit messed up, but there are a lot of products in between. Yeah, I just showed the two kind of extremes. Okay, so let's talk about Flask. As I said, it's a small Python framework that allows you to build web servers. The core feature that it has, that you will be using, is that it allows you to map HTTP requests to Python functions. That's essentially the most important feature that Flask provides. So if a client sends you an HTTP request and asks for a specific resource, then you can say if a user calls the trips endpoint, then I want this function to be called. If the user calls the getUser endpoint, then I want this function to be called. So just this mapping between the HTTP requests and your Python code is one of the core features that we're going to use. And the cool part about working with Python and many other scripting languages is that there are a ton of libraries out there. So specifically for Flask, there are a lot of libraries that we're going to use that speed up development and make it pretty easy to build an HTTP server. So we talked about databases. We talked about client-server communication. The last big chunk that I want to talk about is about defining a server API. So essentially, when you build a server application, it is nothing else than building an iOS app or building a website. It's just a piece of application code. And there are a ton of different ways how you can structure that. And a lot of people have come up with a ton of different solutions in the past. But we want to use a little bit more established one to kind of guide you in a way how you should structure your API. So the solution that we will use is the one that is still most widely used out there in most applications. And that is the approach called RESTful web services. You can look up the terminology. REST means representational state transfer, I believe. It's not too important, but essentially, it is the one that has been established over the last couple of years and is used by most companies out there, so I think it makes the most sense to teach this approach. What do RESTful web services look like? They have a few key characteristics. The first most important one is that the server does not store any state between multiple requests. That means if I have a client application and I want the server to perform a certain task or to send me certain data, I have to issue an HTTP request that has all the information that the server needs to actually fulfill this request. That means if I have a password and a username, I have to send it along. If I have any information from previous requests, I also have to give that to the server. This makes the server very, very simple because the server gets all the inputs it needs as part of the request and can use all of that information to generate a response. In the past, there have been different approaches where the server also stores sessions and kind of remembers the previous requests that a client has made and then bases the response on these requests. But with REST, we have an approach where the client is responsible for sending all the information that a server needs at once. And that simplifies the API design quite a lot. The web service is structured based on resources. So essentially the approach that the designers of this RESTful approach took is taking the HTTP specification that you basically use every day when you interact with your browser and websites and build an API based on that. You'll see the details on, I believe it's the next slide. So each request to a RESTful web services consists of multiple fields. The first one is the URL that identifies the affected resource. So if I want to get the users of my application, then I make an HTTP request to myapplication.com/users. So I just define the endpoint by the name of the URL. Then I have an HTTP method, and we'll see a table later on that maps these different HTTP methods and assigns some meaning to them. But basically there are different ones called, for example, get and put, and these inform the server about what I want to do with this resource. If I send a get message, I tell the server I just want to retrieve information. If I send a put message, I say I want to update the existing information with this information that I'm giving you now. When I send a delete message, I say I want to delete the resource. So also here the terminology is pretty simple. Additionally, I can send a request body. So for example, if I want to store something on a server, then I will send the information as part of the body to the server. Here's an example of a RESTful API based a little bit on the trip planner project that you will be building. It's a fair amount of information here, but let's try to break it down. On the left-hand side, you can see resources. And we have examples of two different types of resources. The first ones are called collection resources, and the second one are called element resources. Collection resources are basically just collection of different objects. So if I want to access all users, or if I want to access all trips, that would be a collection. And I detect a collection resource typically by just having a name and not an appended ID, like in the element one here at the bottom. So with a collection resource, I have multiple ways I can interact with. And here you can see the different HTTP methods that allow for different types of interactions. For example, if I say I want to make a GET request to the trips collection, then the server should respond by returning all trips that the server has stored. If I do a put request to this collection, then I say I want to replace this entire collection with a new collection that I'm providing to you. On the other hand, we can also deal with individual elements. So here at the bottom, we identify an individual element by a specific identifier. You can see it looks different because I have a URI called trips/18. This means I want to interact with the trip that has the identifier 18. And here I again have the same HTTP methods that I can use to interact with this trip. If I use the get method, then I get a representation of this specific trip that I asked for. So I only get one trip that had the identifier 18. I don't get a list of all the trips. If I call put on this endpoint here, then I only replace this one item and not the collection of items. And if I would call delete on here, then I would delete this specific item. So the two essential differences are collections that represent multiple items and elements that represent only one item. And then I have the for and some more HTTP methods. These are the four most important ones that allow me to interact with either elements or collections. More or less clear? Yeah. Why can't you post on a single element? Because the semantics that have been defined are that you post to a collection, where you say I want to add an element to this collection, and then you get the ID that the server assigns to the new object back. So if I create a new user, for example, then I would call /users with post. Then the server would create a new user and would return me the user record with the ID. And then in future, I could interact with this individual element. But the idea behind the element URI is that I always have to provide an identifier. And if the object doesn't exist on the server yet, then the server won't have an identifier which I can use. That's why when I create an object, I have to call it on the collection. Does this make sense? OK. So there's a lot of information in here, but as you get started working with it, I think it will become more clear, and this slide should be a good reference. So I'm almost at the end, but there's one last thing about how you should approach development for the server. And that is an approach called test-driven development. It sounds very complicated, but it's actually not that complicated for this simple type of application. So actually, building such an API is one of the simplest apps you will probably ever build. And that's why it's a great way to try this test-driven development approach with this simple app. The idea behind test-driven development is that you write a separate program that tests your application, and you write that program first before you actually write the application that implements your functionality. So you start by writing a test, and that test will run your app and perform a certain input and then expect a certain output. And then you write the application that actually implements that. The cool part about that is that while doing that, you basically specify your entire application. So when you look at the tests, you will see all the expectations that you have of how your application should work. Let's say, for example, I want to call the user endpoint with a post method. Then I expect a new user account to be created. That will be at one of your tests. And a future developer will come and look at these tests, and then it will see the entire functionality of your server just by reading through the test records. So that's a really cool way of specifying your application. The process is that you first write a test. So you basically write a piece of software that runs your application, performs a certain input, and expects a certain output. Then you run that test, and because the application doesn't have the feature you're testing for yet, that test will fail. And then you go into your application code, and you actually implement the feature. And after you have implemented that feature, and you believe that you've basically wrote the code that makes the feature work, you run the test again, and then you should see that the test now runs successfully. And the cool part about this is you now have specified exactly how your application works, and you can easily refactor the code that you use for the implementation later on. And it happened to me hundreds of times since I used this approach, that basically half a year after I wrote a feature, I basically changed some new code, or I changed some existing code to adopt for a new feature, and thereby I break one of my old tests. So because I make some change, and I didn't think about how that would affect some old piece of code, I wouldn't have realized that if I wouldn't have tests for that. But since I wrote tests for every single feature, I will see that a test fails, and I can investigate which change I made that broke my old code. So a really cool approach, and writing the server is a great way to start using it because it's a very simple interface that you're testing. So then after that, you can refactor your code, and you run your tests again. And from now on, you're confident that your application is still working as expected, and you can always change your code without worrying that you're going to break features. Another cool reason to use that test-driven approach for writing this Python server is that it's just the fastest way of testing if your endpoints actually work correctly. So instead of opening a browser and calling the endpoints and entering data all the time, you just once write code that tests these endpoints, and it's a much faster way of developing your server API. And I'll have instructions in the tutorial on how to do that. Cool. Just in terms of terminology, this process is often called red-green refactor because the tests first fail, then they pass, and then you can refactor the tests and the code. Just so you know what tests look like, they're essentially just Python code. And I have, as part of the template project, already written the first test. But this is what a very simple test could look like. What I do here is I call the server API with a GET request. I specify which endpoint I'm calling, which is the user endpoint. And I provide some headers in this case. I provide specifically a wrong username and a wrong password because I want to test that the server tells me that these credentials are incorrect. So that's the first part. I call my application, and then I receive the response. And the second step is validating this response. In this case, I say I want a status code of 401, because that is the specified status code that says you are not authenticated to access this resource. And then I use an assert statement to check that the response is actually matching my expectation. And when I do this here, then at the beginning, when I have not implemented this endpoint, this test will fail. And once I've written code that checks the username, checks the password, and returns 401 if the password and username is incorrect, then this test will pass. So tests are just additional Python code that run your app and expect certain outputs. Cool. To summarize that, at the beginning, we talked about a lot of stuff. We started out talking about the architecture of our server. And I mentioned that we're going to use a 3-tier architecture, which means we have a client, a server, a database. And our server is going to be fairly lightweight, as in it will mostly just store information on the database and receive that. We're going to implement a server with Flask, and we use the database called MongoDB. We're going to implement a RESTful web service, and we just talked the last few minutes about what the specifics of a RESTful web service are. And that is going to be consumed by the iOS app. And if possible, you should try to approach this with test-driven development and write automated tests first, and then implement the server functionality. Cool. A question mark in your face, Hero? No? OK. So to get started, basically the lecture is uploaded, and the tutorial that goes along with it is uploaded too. You should have a starter project as part of it, and yeah, the documentation and the starter project should help you to get started. Thank you.